Good. We can just have reciprocal.
What? I know.
All right, great. So let's get started. Let's kick off the day today with Yuval, who's going to tell us about a new way of computing unencrypted data using secret codes.
Okay, thanks, Daniel, and thanks to the workshop organizers for putting together a really interesting program. So I'll talk about actually two joint works. Both of them are on ePrint if you're interested in more details. The first is with Tsaitsai, Tamer, and Alon from Bocconi University. And the second is additionally with my current AWS team members, Fabrice, Shai, Hugo, and Tal. Okay, so a secondary theme of this workshop, in addition to obfuscation, is new assumptions. We've heard already quite a bit about new assumptions in earlier days, and we'll hear more about this today in later talks. And I guess one question we should ask is, don't we have enough crypto assumptions already? Why? Why do we still need to make new assumptions? Well, I'd like to highlight three different reasons why we sometimes still make new assumptions. The first is just to sleep better at night. Okay, we want to have more baskets for our crypto eggs. Thankfully, now you don't need to violate copyright when you generate pictures. The second reason, or a second reason, is that new assumptions often come from very fruitful interactions with other fields. I think the next talk by Tzlil might be a representative of that, but there are many, many good things that happen when we interact with other communities. Importing techniques from one area to another. But by using conjectured hard problems from other fields, we're creating this quite unique win-win situation that either our systems are secure or good things happen in another community, which is great. But finally, sometimes we introduce new assumptions just because we want to get new conclusions. Okay, by new conclusions, I mean really new, that even if you combine all existing assumptions, standard, non-standard, and throw in ideal obfuscation, which captures what we can heuristically achieve by I/O, we could not get these conclusions. Okay, this is what I mean by new conclusions here in this talk. Okay, and I guess that this talk is motivated by all of these. This talk will introduce new assumptions, which have all three sources of motivation, but mainly the focus is on achieving new things we could not achieve before under any other assumption. And specifically, we give what, as far as we know, the first example for a non-trivial cryptographic task where security is for free in the sense that the ratio between the computational cost of realizing some task securely and realizing the same task insecurely can get arbitrarily close to 1. This is not about communication. This is really about computation. And my statement is actually insensitive to the computational model. Okay, so it's kind of like, almost like, achieving cryptographic security is for free. In practice, we approximate it pretty well. Okay, it's not for free, but for sufficiently large but still realistic size instances, the extra cost is very small. Okay, so this is the new conclusion that motivates our new assumptions, but I'll also tell you about some results that we can get from old assumptions. It's not just about new assumptions.
About your older work with Ehrlich, where you had linear time or...
Yeah, I mean, there is a line of work, actually quite a few works that achieve constant computational overhead, but there you have some multiplicative constant. Here we have just sublinear additive term. Okay, so I want to start with a story that will both introduce the specific question that motivates this work, and also, I guess many of us can relate to how it sometimes feels when you try to make the real world use advanced cryptography. Okay, I think many of us over the years have had similar experiences, so I'll kind of combine both with one story. And the real world here is represented by this somewhat passive-aggressive software engineer. And this is an optimistic, upbeat cryptographer. And again, the story, the application here is straightforward. We have our encrypted data, emails, whatever, stored on the cloud, and we want to search it without decrypting it. Okay, that's kind of a straightforward crypto application. And yeah, so the cryptographer asked, want a cryptographic solution? Of course, initially, yeah, bring it on. Okay, good. So what cryptographic solution? How about searchable symmetric encryption? Right, you know, practical, works great. Well, are you kidding me? It doesn't support fuzzy searches, the type of searches I need, and it leaks the access pattern. Okay, this is standard searchable symmetric encryption. You know, these applied people sometimes know just enough crypto to shoot us down, right? Not more than that. Okay.
Stories.
Let's move on. Then it looks like you want homomorphic encryption, abbreviated as HE. Okay, get real. You know, I don't have time for this. Got it. Okay, so what you probably want is honest majority secure three-party computation. It's very fast. Okay, and here comes the point where you always get to this point. I don't like non-collusion assumptions. But come on, you make non-collusion assumptions all the time. I can show you where you're making them. I don't care, can't make them here. Okay, so this is kind of a typical conversation that goes again and again.
This you know from your experience at Amazon?
No. This is just completely a generic story. And okay, so now the cryptographer starts thinking, right? It seems like a deadlock. That's it. We're stuck. But I actually but cryptographers never give up, and I actually got a real footage of, you know, this is like an MRI footage of a cryptographer's brain at work. So watch this closely. This is how cryptographers tries to solve a hard problem. Okay, and then there is the eureka moment. Wait, I have a solution which is as secure as homomorphic encryption, is even faster than 3PC. Okay, like achieving the impossible. Okay, so now it's the real world's turn to think. Now this story has two possible endings, and you know, the first ending is sometimes the realistic ending, but we all hope for the Hollywood ending. Okay, so yeah, so that's kind of introduces the problem and some competing solutions and what we achieve. This is kind of a summary of the non-technical summary of the talk, but now let's get technical. Okay, good. So let's have the most straightforward modeling of computing on encrypted data in a secret key setting. So we have a client and a server. The client holds a secret key, a short secret key. And there is an offline phase, which is done once, and then an online phase that can repeat an arbitrary number of times. So in the offline phase, the client has, think of a big chunk of secret data, X. So I'll use the color code where red is secret, green is public. The client encrypts it using the secret key and uploads X hat, the encrypted data, to the server. Okay, this is now the client can erase X and just keeps the short secret key. In the online phase, we can have polynomially many instances of the following interaction. The client still has its secret key, that's all it has. Now the client wants to query the data, say do some search, QI. It sends to the server an encryption, Q hat I. It's green because everybody can see it. The server does some local computation from the encrypted data and encrypted query. it computes and sends back an encrypted answer, and the client uses the secret key to find the answer to the question. Okay, so this is the kind of the mechanism, the functionality. Let's talk a bit about security. We want the server to learn nothing about the data and the queries, okay, except their size. So this is the straightforward security. Again, here I'm assuming everybody is honest but curious by default, but adding malicious security to our solutions is quite easy, yes?
Okay. I'm trying to understand why you made the choices you made. So you're going from offline to online.
Yes.
And, okay. And with the process now, you've also introduced a difference between Q and X. What should I be thinking about it? What is X and Q in the online stage?
So X are, say, my emails or documents that I encrypt in the cloud. Okay, I don't keep it on my device, yes. Think of the server as the cloud.
Before.
Yeah, the server is one party, but since it only processes public information, you can think of, a fleet of computers. It doesn't matter, right? So the server is just the cloud. You can think about it this way.
So you've done the offline stage, you gave it everything, and now you're saying, as my X in an encrypted fashion,
Exactly.
I would like to make questions.
Yes. Good. Okay, so this requirement is a distinction with the usual notion of searchable symmetric encryption, where there is significant leakage about the queries. We do want both the client and the server to be stateless in the sense that they don't have any evolving state. So throughout the online phase, the client only needs a secret key, the server only needs the encrypted X. So this rules out oblivious RAM. And in terms of this is the minimal efficiency requirement I will make, is that the download cost in the online phase is sublinear in the size of the data. Yes?
But your encryption could include something. I'm thinking like your connection with searchable encryption. If you have some sort of encrypted index or something like that, that will be fine if I can think of it as a one-time part of the encryption.
The encrypted X, I don't make any requirements. Yeah, it can be an encrypted index.
You can have some data structure built on top.
You could have everything. I mean, we will not use it for our functionality. Okay, anyway, so we have this non-trivial efficiency requirement, which says that the download is sublinear, and this rules out using classical techniques for secure two-party computation that will have linear communication. Okay, they achieve all requirements except for sublinear communication. Okay, so this is kind of positioning the model and how it rules out certain previous approaches. Okay, and we look at two functionalities. The first is private information retrieval. Here, the data, we think of it as an n-bit database, and the query is just a lookup to a single index I in the database. This corresponds, here the database is encrypted, but that's easy to achieve. So this corresponds to the previously studied model of secret key PIR with preprocessing, okay, where there's a client that encodes the database and later can use the secret key to make queries, which was studied with Boyle, Pass, and Wouters and independently by Canetti, Holmgren, and Richardson. I should note that this is weaker than what is usually desirable, which is the public key version. And there was a recent breakthrough introduced with the work with Baimel and Malkin, and there was a recent breakthrough by Lin, Mook, and Wicks. And yeah, so this is, of course, a big difference, secret key versus public key, but I'd like to point out that in many settings, the secret key setting is good enough. One such example is secure multi-party computation, where we anyway distribute the secret key. But there are also other situations where we need to distribute the secret key. For instance, if the data is secret, is encrypted and not owned by a single client, then we need to do some threshold decryption, which is often the case in applications of FHE, for instance. So if we do threshold encryption, why not do threshold? If we do threshold decryption, why not also do threshold encryption, where we distribute the secret key? Okay, so I think it's fair to say that For many use cases, the secret key version is good enough, and in fact, if the encryption process is easier to distribute in the secret key version, maybe we're better off. Okay, because, yeah.
And you insist on preservation RAM complexity, right? Because otherwise you don't need any of the stuff like homomorphic encryption ones, right? So it's just
yeah, I'll talk about homomorphic encryption. Yeah, homomorphic encryption definitely works.
Also, so you actually you're okay even if the query is like binary search, you're okay to read all of that. So the time of the server doesn't.
I'll talk about it in the next bullet. Yeah. Okay. So the typical goal, great question. The typical goal is to get a so-called doubly efficient solution, where doubly efficient refers to the RAM model or the cell probe model, which is the data structures version of this model. And when I refer to efficiency goals, computational efficiency, we change the metric. Okay, we look at minimizing the Boolean circuit size of the server as a function of X hat, the encoded data, and the encrypted query. Okay, it's a different metric. Does this metric make sense? Well, both metrics make sense. But I should say that the typical theoretical modeling, views this operation, a single RAM access, as being exponentially or infinitely faster than this operation, mod 2 inner product. Why? Both are implemented by linear size circuits and log depth. If you look at the silicon, something like this. I'm not saying there is no difference. I'm just saying there is not an infinite difference. Okay, so I think both metrics are interesting, yes?
Sorry, I missed your point. So if you think of it as a circuit model, then going back to Evgeny's point, it's always you have to look at all the backs if you're thinking of a circuit.
Yeah, sure. But I'll tell you, I want to minimize the circuit size to the extent possible. Right. And I'm not requiring sublinear circuit size. I want to minimize circuit size. You're right.
Okay.
Circuit size cannot be sublinear in N. I want it to be as close as possible to N.
I see. Okay, so you're not really talking about double efficiency here.
It's not double efficiency. It's just minimizing, it's minimizing circuit size. Okay, this will be the efficiency goal. There is also, even without this efficiency goal, the questions I'm asking are not trivial. Okay, so again, I think that if you consider new architectures such as GPU, maybe we're shifting a bit more from the RAM model to the circuit model, but again, I think the truth is somewhere in between.
Just to check, double efficiency would imply like linear, like optimal circuit size as well, right? Like
up to a huge constant, yes. But it depends on the encoding size, because we measure efficiency in terms of the data size, not the encoding size. So if you're blowing up the encoding by a polylog factor, then you're blowing up automatically the circuit size. But Okay, so the second functionality I'll talk about is what we call an encrypted matrix vector product, and here it's just what it sounds. Here the data, I think of it as a matrix with M rows and W for width columns. You can typically think of M as being much bigger than W. I'll soon give an example for motivating application. And the query is just a vector, and the answer should be X times Qi. Okay, so we're just uploading a huge matrix, and then in the online phase, multiplying it by vectors. And typically, this is not the exact functionality we want. Typically, we want to do to compute some partial information about this matrix vector product. But because this matrix vector product is highly compressive, this post-processing step will be dominated by the matrix vector step. Okay, so this is, and in this talk, I will focus on the second functionality, which in some sense implies, I'll also talk about what we get for PIR, but in some sense, it implies solution for PIR. Okay, so to give a sense of applications of this EMVP primitive, so these are two papers from last year that both involve proving uniqueness or preventing people from registering twice to the same service. And how do we enforce it, right? What prevents me from registering twice to the same service? Well, the service provider can have a data bias. So this is based on biometrics, okay? For every person, there is an associated vector that captures some biometric information. Okay, so this matrix, each row of this matrix represents the biometrics of an existing user. And when a new user comes to sign up, the matrix vector product measures the similarity of the new user to each existing user. And if the similarity is too big, then the user is disqualified, right? It's not allowed to register. It's already in the system. Okay, so this is the motivating application for both of these papers. And just to give you a sense, so this second paper, by the way, this second paper captures a solution by World ID, which is some initiative of Sam Altman. It's a pretty high-profile, endeavor. And they use iris scan for the biometric information, and at least in their implementation, the width of this matrix is around 10,000, so it's very wide, right? So obviously, when you multiply it by a vector, it's extremely compressive. Okay, and what kind of solutions they employ? Well, the first paper used homomorphic encryption and also garbled circuits, and the second paper really observed that if you use honest majority secure three-party computation, you'll get a much, much, much faster solution. Okay, and even earlier work by Alexandra and Emma and Henry and Nikolai considered a somewhat different setting where the matrix is public. And in this case, they used linearly homomorphic encryption to realize this functionality where the motivation is document search, okay, either searching a web page or an image. And here, so here you get solutions based on linearly homomorphic encryption, which can be optimized and is faster than we think it is. Okay, so let's discuss the feasibility question of how can we build EMVP, or from what primitives, from what existing primitives we can get it. So the natural approach is to use homomorphic encryption. Note that because both the matrix and the vector are encrypted, here we need actually homomorphic encryption for degree 2 polynomials, which was first given by Bonet-Nissim and later was implied by homomorphic encryption solutions, general homomorphic encryption solutions. And a natural question is, can we do with linearly homomorphic encryption even though the data is encrypted? Okay, and as I said, this is simple when the data is public, when the matrix is public. So it turns out that there is a simple generic transformation that uses masking. Okay, so we can take the original matrix X, mask it with a pseudo-random matrix R, and now we upload, and now we take this masked matrix and we apply the previous solution, right? The public matrix solution to X hat, okay? Because X hat is masked, then there is no risk in revealing it to the server. And now the client just needs to take the answer X hat times Q and unmask it by computing R times Q. Okay, so from a communication perspective, this works well. The issue is that the client computation, if we do it naively, this R times Q will require the client to do as much work as doing the computation on its own, and we can get around it using a very interesting new primitive called trapdoor matrix, which was independently introduced by Braverman and Newman and by Vaikuntanatan and Zamir. Okay, so trapdoor matrix is a primitive that allows us to generate a pseudo-random matrix together with a trapdoor, where the trapdoor allows us to do matrix vector multiplication fast in linear or near linear time. Okay, so I'll not get into these constructions. I'll just say that these papers gave feasibility results from standard LPN assumptions. In our paper, we have a section that shows more practical approaches to implementing this primitive.
On the same assumption?
No, under different assumptions.
What's the assumption?
So there is a generic dual LPN, direct construction from a dual version of LPN. So if you use, for instance, ring LPN, you can have a very simple direct construction. And then we have even more practical constructions from MQ style assumptions, like multivariate. Basically, is that multivariate cubic polynomials are pseudo-random. Okay, so I want to talk about another feasibility feature of that is desirable in our solutions achieve, and this is being field agnostic. What do I mean by being field agnostic? It means, again, we have a finite field here, but we don't even have a description of the final field. We only have access to it as an oracle. So the inputs, you can think about it kind of like a generic model, like a generic group model, a generic field model, except that our inputs are taken from the field. We can perform field operations, addition, multiplication. Sometimes we need inversion, but we can sometimes avoid it. We can sample random field elements. That's it. Okay, we cannot decompose the field element into bits. So there has been previous work on secure computation protocol. So this terminology, by the way, is borrowed from the proof literature. They have field agnostic protocols that work over any finite field, not necessarily FFT-friendly field. Yes?
Am I allowed to know the size of the field?
No, you do not, in our solutions, you do not need to know the size of the field. Yeah, you just need to be able to sample random field elements. So this was shown, so if we look at the honest BGW style protocols, honest majority setting, they natively satisfy this feature. If we look at these honest majority protocols, this is harder to achieve, but was achieved under LPN style assumptions, first by Naor and Pincus, and then by follow-up works. And I should say that if we look at the domain, the entire domain, forget about EMVP, the entire domain of sublinear secure computation, of arithmetic computations, there were no previous field agnostic solutions. So all of the previous solutions that I mentioned are all kind of circuit-based. And if you look at lattice-based solutions, they don't achieve that. For starters, the rounding operation that you need cannot be cast in this field agnostic model. They also usually move to, if your plaintext field is FP, you have to move to a bigger FQ in the ciphertext domain. So these are reasons why lattice-based approaches are not agnostic. And in fact, in the same paper by Appelbaum, Avron, and Bruschka, they have results that imply that solving this problem without preprocessing, so if you just want to have linearly homomorphic encryption, which is field agnostic, this is impossible. Okay, so we don't solve linearly homomorphic encryption, we relax the problem. Okay. And why do we care about being field agnostic, besides being a nice feasibility result? Well, it correlates empirically with concrete efficiency. This was also the original motivation. And also, I think a big advantage is that the query generation and the post-processing by the client can be easily distributed, even in the malicious model. So using classical techniques from MPC, we can really easily distribute clients, which is useful. And this is much harder if you need to do Gaussian sampling and rounding and so on. Okay, so that's it. So let me describe our results and then the solutions. So for the EMVP problem, from a feasibility perspective, we show that under LPN, standard LPN over big fields, the same LPN that we heard about in the obfuscation talks, in JLS, we can get field agnostic EMVP. In fact, even in noise regimes where LPN is not known to imply public key encryption or collision-resistant hashing. And from an efficiency perspective, we can get everything to be optimal up to polylog factor. Okay, so it's some kind of a sanity check that EMVP can be solved in a field-agnostic way from standard assumptions. Not only standard assumptions, but assumptions that lie between Minicrypt and Cryptomania. But I think the more interesting, and this relates to the new conclusion from my opening slide, is that we can get really the security for free feature. Here we need a new assumption, which is a new variant of an old assumption by Dodi, Scalai, and Lovett called learning subspace with noise. I'll talk about this assumption. And here again, even for realistic matrix sizes, we can make the overhead very small, 10%, 20%, that's practical. Okay, and this is of course based on cryptanalysis, so part of our effort is to cryptoanalyze the underlying assumption and suggest concrete parameters. Okay, any questions about the result? Okay, for PIR, again, we can show a feasibility result of achieving n to the epsilon communication for any epsilon. Okay, so very sublinear. Again, based on standard LPN. And this shows that if we don't insist on double efficiency in the raw model, then we can get sublinear communication in the secret key model, again, using these intermediate assumptions between Minicrypt and Cryptomania. And there's a really nice recent work by Lin, Mook, and Wicks that gives evidence that doubly efficient PIR cannot be based in a black box way on one-way functions. Okay, so this still leaves open the question of what if we don't require double efficiency. That's still open, but it's reasonable to conjecture that one-way functions are not enough.
So, sorry, so your LPN here is also the LPN with parameters that does not imply
Yeah.
public encryption?
Yes. And
the NPN parameter regime is not, we don't know that implies. That's,
Yeah.
that's,
yes, yes. That is not known to imply it, but many tried. It's not just not known.
yeah. We tried it once and it implies.
Okay. So here we minimize, I mean, previously I said that we get security for free, but this applies to arithmetic computation over a big field. Here we're working in the Boolean circuit model, and here we have a 2x overhead compared to the plain text. So, if you just want to do selection, this requires 2 AND gates. Now I'm talking about the full B2 basis. So XOR is one operation. And we get circuits which are twice as big, which are roughly of size 4 times the database. Okay, so it's very close to optimal, 2x. Yes.
Known, there are many like polylog PIRs which are not even secret keys. Here's assumptions. So what are the best assumptions for normal PIR? Right.
The best assumption for standard PIR, it implies oblivious transfer or public encryption. So standard PIR implies public encryption, and here we use an assumption which is not known to imply public encryption. Yes, so again, this high efficiency result also relies on a new variant of this LSN assumption that I mentioned. Okay? Cool, so let me describe the solution. It's very simple, and it's based, as the title suggests, the solution is based on a pair of secret dual linear codes. Okay, there is one code which is the query code, which is used to encrypt the queries, and one code which is the data code, which is used to encrypt the data. So let's start by looking at the data code. Okay, so let's say that we want 25%, we're okay with 25% overhead. Okay, so then this is the data code. We write the generating matrix in a systematic form. Okay, this is like we encode a row of the matrix by multiplying it from the left with this, multiplying it, with this matrix. So, so think here of K as being W over 4. Okay, so we kind of, the encoding expands by 25%. Think of it as a systematic code which copies the message and adds 25% additional parity checks. This is the data code. And the query code is just the dual code. Okay, so its dimension, will be k. And how do we pick this code? It's crucial that these codes are secret. So the conservative choice is to just use a pseudo-random code. And in fact, this is good enough for...
Random code in the sense,
No, not in the new sense, but in the traditional sense, which is defined by the secret key of the client. But if we want to minimize the cost of encrypting the query, which is dominated typically by the server's cost, if we want to minimize the cost of encrypting the query and the setup, then we want to use structured codes, as in ring LWE, ring LPN, and so on. So there are many different options of codes, but the most conservative choice is to pick just a random linear code or a pseudo-random linear code. And the protocol goes in the following way. In the offline phase, we encode our matrix, multiplying it by D, and we mask it with a pseudo-random matrix R. Okay, this is the offline phase. We just take each row of our matrix X, apply the data code to it, kind of like adding 25% of parity checks bits or redundancy and masking it. Okay?
So are you thinking of X as being W times W? What should I?
X is just a matrix of width W and many rows M. Okay, so X has many rows. Each row, we encode it using the same code by adding 25% extra symbols.
You're saying D, if I want to think of it the simplest way, is identity and then a random D prime.
Exactly.
Okay.
Yes. Mm-hmm. Yeah, I'm just writing the systematic matrix. Without a lot of generality, I can write it in systematic form.
D is known. Who knows D?
D is secret. Both D and C are secret. Yeah, these are the client. The client knows D and C.
The secret I can
Yes.
I keep it to myself. And
Yes.
then I send you this X hat. R is I keep to myself. D I keep to myself.
Exactly. Yes.
X is specifically to your data, and D is specifically to your secret key.
D is specified by the secret key, exactly.
Do with the data.
No, exactly. Yeah, so you can...
It's not public, of course.
Yeah, that's secret. Exactly. So you can think of this X times D as being X padded by 25% extra columns where each, row is encoded. Okay, yeah, and this is pseudo-random matrix determined by the secret key. Okay, in the online phase, the client does the following. He takes the query. This is the vector that he wants to multiply X by, pads it with zeros, and adds a random code word in the dual code C. Okay, this is the query code. Okay, now it's easy to check that if you take this QI tilde and multiply it by X times D, then QI, right, if I go back, the QI multiplies the X part. Okay, so this is the functionality we want, QI times X. And the zero part cancels out the X prime part. Okay? And now if I add CI, which is a code word in the dual code, this is why we use the dual code. This cancels out because D times CI is 0. Okay, but there is still this R times Q tilde I, which is noise, but this is noise that is known to the client, right? Because the client computed both.
So you use
terms.
R as the trapdoor kind of? So you can do
Exactly, yeah. So I'll get to this soon. Yeah, exactly. Okay, but let's first describe the protocol. So the client will send Q tilde I. The server just does matrix vector product, the same functionality, but on the encoded matrix and the encoded query, encrypted query. And then the client can unmask using R and Q tilde I. Okay, so this is the protocol. Let's look at the efficiency. So the efficiency, both in storage and the communication, the upload is determined by the rate of the code. So here in this running example, it's 25% overhead, right? It can be made 1%. And there is no download overhead. Okay, we just get one field element for every row. Okay, it seems a bit too good to be true at this point. Is it too good to be true? Is this okay? Anything here looks problematic? Okay, let's talk about computation before we discuss security. Right, so this is the bulk of the work. It's done by the server. It's a matrix. It's a huge encrypted matrix times a vector. But again, the overhead here, because we only make the matrix slightly wider, the overhead here will be, again, 25%. And then there is this problematic part. If we want the client to be efficient, then we'd better have some solution. And as Yael suggested, here we can use a trapdoor matrix.
And every time you do this, you need to choose a different random R, right? Because otherwise...
No, it's the same R. It's the same R. It's just that you apply, the trapdoor allows you to multiply the same R, but then you'll multiply the same R with a different Q tilde I every time.
Won't that harm you security-wise?
No, because the server doesn't, from the server's perspective, it just gets a pseudo-random matrix.
No, but if you give him X hat, which is XD plus R, and then you give him another...
No, the query does not depend on R. The query does not depend on R. Yes,
yeah.
Just once, yes.
Usually for like related models like CCA secure encryption, you give full decryption oracle. You don't just like call decryption oracle and don't give the result to the attacker, right? So keeps international, the attacker should learn out of the queries. And in this case, it still doesn't learn. And then he will learn R times QI, right?
I mean, you can do post-processing that will just reveal the output to the client. I mean, you can do secure post-processing that will realize the ideal functionality of the client.
So you're saying in this model, the server is kind of really outside, he doesn't see what client does with the results.
Yeah, it's just a standard model of semi-honest security, and you can easily upgrade it to malicious security with very low cost. Okay, so what about security? We're already happy with the efficiency part. Should we also be happy with the security part? I said our solution is simple, but it's not that simple.
So far, you're just doing linear algebra, no? I mean...
Exactly, yeah. Well, I kind of promised that I promised a field agnostic solution. So we don't do much more than that, but we do a little bit more than that. So here, if you notice what's going on, you don't really get semantic security, right? Because if all QIs are the same, okay, again, this generalizes, but just as an example of why this is not semantically secure as is, if all QIs are the same, then the rank will be at most the rank of this query code plus 1. Right? Because, this is the only source of entropy, and this is taken from a k-dimensional space. So all of these Q tilde I will be taken from a k plus 1 dimensional space. And if we have enough of them, because k plus 1 is less than n, there'll be an attack. Okay, and it might seem like a benign attack, but it can actually be devastating. Okay, so we need to do something else. What do we do when standard linear algebra fails us? We add noise, but the kind of noise we'll add here is different. Okay, so we want this Q tilde I to be pseudo-random. And now this is how we solve the problem, or at least we think we solve the problem. So we add noise, but what kind of noise? If we try to apply the standard noise of LPN or LWE, like either add a small number to each coordinate or make 1% of the coordinates random, this will hurt correctness. Okay, this will not work. So instead, we use two alternative types of noise. The first kind is what we refer to as a mixture noise, which means that, again, recall that we have this secret code C. This is the query code. That the security experiment, or in the protocol, we either take the real query we want to make, or with some probability mu, we sample from a different distribution. For instance, a uniformly random vector. This is a mixture noise. Okay, the protocol will still work even with mixture noise, except that every once in a while, or maybe most of the time, the client will get junk, but the client knows that it gets junk. So we don't even need error correcting codes. It's enough to use erasure codes.
But you're saying with some probability, I'm going to actually give you my Q in the clear.
Exactly.
And with some probability.
Exactly.
But that's also LPN. You can think of it.
But here we make everything noisy. In LPN, you make some coordinates noisy. So here it's a dichotomy, either no noise or total noise. Okay?
Vector version.
Mm-hmm. Exactly. It's a vector version of LPN.
Yeah, known as LSN. Okay, so this is, but again, LSN is a specific kind of mixture noise. It will be useful to also consider others, right? It's kind of like distractors. Okay, adding these distractors. And the second type of noise, which happens to have advantages, in particular, gives us the efficiency claims that I made, is what we call a planting noise. So instead of replacing this query vector by something else, we just plant it in some space, low-dimensional space. Okay, so the query will actually be a description of a low-dimensional linear space that contains this Q tilde I that we want. Okay, so if of course the server can just make a list of all possible vectors, and this kind of puts us in the mixture case. But then this list will be huge, exponential. Okay, so again we have I'll make it more concrete soon. But these are at a high level the two types of noise. Dealing with mixture, like modifying the protocol to handle the mixture noise is trivial, right? Because whenever the client makes a noisy query, it just ignores the answer. Okay, and then, if there is sufficiently high probability not to have noise, then the client is happy. There is some overhead, of course, but it depends on this mu probability. Just to spell out how to do it with planting noise, again, this is also straightforward. Now, instead of sending this Q tilde I, the client will send this Q hat I, which is a low-dimensional space picked at random from the spaces that contain this Q tilde I. Okay, and there's also a question of how do I pick this space? I will have two answers to that.
But in the planting noise, there's no junk with some probability. You always plant.
In the junk, in the mixing case, in the planting, yeah, there's no junk. Yes, you always plant. Yeah, at least these are the clean forms. You can have, yeah. So now this is how the modified protocol looks like. I send the matrix that generates this low-dimensional subspace, and now the server multiplies x hat by q hat. And the client knows how to span the Q tilde by Q hat, so that's fine. And it still seems like it doesn't give the overhead I promised, because this space must have some non-trivial dimension, so it has at least a 2x overhead, if not more. So I'll show you how to mitigate that later. Even the 2x overhead we're not happy with, so I'll show you later how to eliminate it. Okay, yes.
So cryptanalytically, how small could you make K and still expect quasi-polynomial security?
So I'll talk about that. In fact, we're not happy with quasi-polynomial security, but we can get sub-exponential security against algebraic attacks. So we have analysis that show, I'll talk about that. Okay, so let's first talk about the simple case of mixture noise, which was introduced, as I said, by Dodis et al. So this is pictorially what's going on. We have this secret linear subspace C. This doesn't change. It's just one linear subspace. In the pseudo-random experiment, we mix samples from C with samples from the entire state, from the entire space. Okay, so it's really a mu mixture of distribution over one linear subspace C with another linear subspace F to the N. Okay, and the random experiment on the right, these are just random vectors, and why are they statistically far? Because we don't expect to have a high fraction of points landing in this tiny space, right? Even if the ratio between k and n is 0.99 n, there's still just an exponentially small fraction of points in the subspace. Okay, so this is a meaningful pseudo-random assumption. And let me tell you a bit about the history. So the original context was feasibility results in leakage-resilient cryptography. And perhaps one reason we don't know, most of us do not know about this assumption, is that later similar results were obtained from a standard LPN, at least from a feasibility perspective. It turns out that the learning theory community, there is a paper by Chen et al. From a few years, they're kind of obsessed about learning mixtures of simple distributions. Tzlil nods. So and uniform distributions over linear subspaces are definitely simple distributions. So this was a paper about the search version of LSN in the context. It's not about the search version of LSN, but this is an instance of the problem they study about learning mixtures of distributions over linear subspaces. And in a sense, one source of support of belief is that they tried to solve it and could not come up with better solutions than what we know. You can think of these 2017 papers on doubly efficient PIR as using some flavor of LSN, just to try to cast. It doesn't look this way initially, but there the data code is a secretly permuted Reed-Muller code. So the only randomness in the code comes from the secret permutation. I give you a Reed-Muller code, and the randomness is a secret permutation. Why Reed-Muller code? Because it's locally decodable. So a more generic version would be pick a random locally decodable code. But the dual code of a Reed-Muller code is also a Reed-Muller code. But instead of picking random queries from the dual code, because of the locality requirement, these papers target the usual notion of doubly efficient PIR. The queries or the code words we sample are conditioned on having low weight. Okay, this is the local decoding property. It means there are low weight code words, and we actually pick random low weight code words. And the noise, there are different variations in the two papers, but the noise is essentially just revealing the places where we have non-zero values without revealing the actual values. And this is roughly the same as what I will later call split LSN. It's a version of LSN. You can think of it as being roughly the same as hiding the low-weight noise in a low-dimensional space. Okay? So I will later define a variant that even gets closer to that. So in a sense, the planting noise that we have is a more generic version of these previous assumptions. And there has been work trying to analyze these assumptions or break them so far without success. Okay, so in a sense, this is another source of confidence. People actually try to break these assumptions. I believe that if one is broken, then the other is likely to be broken as well. Okay, what do we know about attacks? I guess I should be faster. So I should say that when the dimension is very close to n, right? When the code is almost the full space, then we have equivalence to LSN when the field is small. Otherwise, we know the following. So think now of the rate as being 1/2. We can show that LSN implies LPN. The intuition is that if you have to break LSN, the mixture version, you need to find a sparse linear dependency. Okay, because you have these vectors from low-dimensional space, and to find them, it's enough to find a sparse linear dependency, and this you can do with an LPN oracle. But it turns out that there are better attacks on LSN, and in the DKL paper, this attack is attributed to one Raz. And it turns out that you can break it if the noise has constant rate, if the code has constant rate, you can break LSN in quasi-poly time for any useful noise rate. So even if the noise is very close to 1, just polynomially bounded away from 1, you can still break it in quasi-polynomial time. The planting variants we use do not have this. So they could be, and in fact, we give evidence that they're sub-exponentially secure against the same kind of attacks. Okay, so just to give you a flavor of how this run-ras attack works, let's assume that the code has rate 1/2, and the noise rate is 1/3. 1/3 means that with probability 1/3, I replace a code word by a random vector, right? So in this case, it's easy to see that after 3/4 n samples, we will observe the first linear dependency, because then we will have n/2 samples from the linear space, whereas in the random experiment, the linear dependency will only occur after roughly n samples. Okay, so this is a simple distinguisher, but we can get around it by using higher noise rate. But it turns out that if you tensor the samples, then you're working in some tensored code whose rate is much smaller. So this is how we can break this version of LSN. If the code rate is constant, and even if the noise rate is 0.999, it's still broken, but we conjecture and give evidence for security whenever.
So his method does not work once you do the tensoring?
No, the tensoring actually makes this method more effective. So it means that for any constant noise rate, you can break LSN, but if it's close to 1, like if the difference from 1 vanishes, then these attacks require super polynomial time. And this is the best known attack. Also from the learning literature, also, you know.
It requires in the sense that it takes that much time.
It takes that much time, and you can actually capture these attacks in a clean way by finding, so this tensoring attack is equivalent to finding a low degree polynomial that vanishes on the samples. This is what the attack does, and for this, we can prove tightness of the attack, okay, so how do we get the results? Well, I will conclude soon. So just to explain how we move from LSN to LPN, the idea is to have the query code with a really high rate. What do I mean by really high rate? That, you know, this is like sublinear in K, the number of parity checks. And if you write the query code in systematic way, this is how you generate a query, right? You basically pick a secret vector and multiply it by the generating matrix of the query code. So now, if we write it in systematic form, we get this secret linear combination in the clear. And you can think of the columns, the non-systematic columns of the query code as being LPN secrets, multiple LPN secrets. So now, if we add noise rate, which is the inverse of this slack, then, so this is not a mixture noise with a random vector, but it's a mixture with adding noise to the last coordinates. And now we have the situation that, you know, sorry, I'm being a bit too fast, that each row, right, because the noise probability just cancels out the number of columns here, each row will be noiseless with constant probability, which is good for correctness. It means that we have correctness with constant probability, but each column will be non-zero with overwhelming probability, which makes LPN secure. Okay, that's the idea. If you choose these parameters, but this has a cost inefficiency. Okay, so let me just finish by saying, planting noise, there is a simple version where you plant in a random d-dimensional space. And there we can prove that the best algebraic attacks using the same attacks that are known as n require times k to the d. So if this dimension is n to the epsilon, then you get sub-exponential security. But to get our most efficient results, we use a structured space, which is a product space. So basically, let me describe the noise explicitly. It's a special case of this planted noise where we have a product space, which means that we chop the code word into a small number of blocks, and we multiply each block by a secret non-zero scalar, random secret non-zero scalar. This is our noise. And this corresponds to the planting noise where the space we plant in is a product space. And the reason this gives us this essentially no overhead is that now the server, now we basically didn't increase at all the length of the vector, right? Because we just take every block and in place multiply it by a secret scalar. And now the server just multiplies each block by by the corresponding set of columns of the matrix and sends back to the client. Okay, so we did not pay anything or almost anything in storage and server computation. We paid a little bit in the download, in what the server sends to the client, namely the number of blocks, which is small. But we can eliminate it by composing with an inner linearly homomorphic encryption. So we can add another, so you can think of our solution as compressing this super wide matrix into a very skinny matrix. But now we're not happy with sending even a skinny matrix, so we use another layer of linearly homomorphic encryption, whose overhead will be swallowed by the big compression step. Okay, so this is all I have to say. And there is an implementation showing that the concrete overhead for realistic parameters, again, based on our cryptanalysis, is quite small. You really approach plain text computation speed. And let me, so for secret key PIR, we can use folding techniques to get communication down to n to the epsilon. So if you just naively apply matrix vector product, you get stuck at square root n. But you can use folding techniques to get it down to n to the epsilon. From a feasibility perspective, as I say, we show that secret key PIR, if we don't care about double efficiency, just communication being small, it sort of lives in an intermediate world between minicrypt and cryptomania, for all we know. Using a Boolean variant of split LPN, as I said, we have a 2x overhead here, not a 1x. And there is still an open question of making the client's computation fully sublinear. We can only get it to be cubic root of n. But again, you can compose with standard PIR scheme and inherit the efficiency feature of our construction and the client complexity of the inner PIR scheme. So you can sort of get the best of both worlds and eliminate this caveat very easily. Okay, so let me conclude. So this is a new technique for computing on encrypted data. We use, these two dual codes. We can think of it as combining. A big advantage of homomorphic encryption is that the bulk of the computation can be done in an untrusted environment, right? If you have these three non-colluding servers, you need to really protect them. You cannot do the computation as you wish. Here you can use a fleet of servers. You don't care how the bulk of the computation is done. Our clients, because of the field agnostic feature, our clients are super easy to distribute, semi-honest, malicious, using it kind of connects well with these PCG techniques. This is very easy.
Clients, you mean that the query is a combination of queries?
By distributed client, I mean both in the encryption process and the decryption or post-processing process, but I mean that instead of having me own, suppose I don't own the data. It's an encrypted biometric data of many people, right? So the secret key cannot be held by anyone. And you have instead 11 servers that hold shares of the secret key.
They share.
Yeah, and whenever I make a query to
the original X.
Yes, and then you use classical secure computation techniques like BGW-style protocols or GMW-style protocols to distribute the query encryption, which is very fast and very simple because of this structure of the protocol. Okay, we get these feasibility results from standard LPN, sort of like a sanity check, that we're not asking for too much, at least in the context of being field agnostic, or in the context of not using public key crypto, right? So this we know based on standard LPN. Again, we would have much less confidence if it weren't for this feasibility. And again, security is essentially for free based on new LSN style assumptions. Yeah, so the bulk of the work, if you look at the bulk of the work, starting from a certain reasonable.
It's not much more expensive.
Yeah, like the ratio can get arbitrarily close to 1. Yeah. And this doesn't happen for matrices of width 5 billion. This happens for matrices that are, few hundred width. So we can get like practically 25%, 10% overhead for practical instances of the problem. Okay, there are many open questions. You know, if we consider the feasibility question, you know how to do it from LPN. Can you do it from one-way functions? I chatted with Daniel. He believes the answer is no.
What about the result you mentioned?
So the result insists on double efficiency, so sublinear computation time in the RAM model. By the way, we can get it under LSN, we can get slightly sublinear server computation, but this can be actually practical. LSN assumptions, we don't have search to decision. This will simplify and improve the results in the learning paper that I mentioned, if you can find such a reduction. More relations between LSN and LPN, so we can relate the basic version, the mixture version of LSN to LPN in one direction. We don't know a similar relation for the planting version. Better understand the relation with the permuted Reed-Muller code assumption, which gives us double efficiency in the usual sense. And also more concrete analysis. We actually spent quite a bit of effort in the EMVP paper on concrete analysis, ran it by a bunch of relevant people. You know, definitely more time needs to pass and more people need to look at it before we get full confidence. You can extend it to, say, modulus Z2 to the K, right? These things we haven't analyzed, but the extensions seem to be okay. And there's a lot of questions in the context of applying this. So this is just a core primitive, and there are many types of extensions you might want to have. That's it.
We're a bit over time, so let's take questions offline.
Yeah.